So let's talk about volumes. Many solid objects, especially those made on a lathe, and a lathe is pictured here to the left, have circular cross sections and curved sides. In this section, we will see how to find the volume of such objects using integration. So in the last section, we learned how to define the area under the curve using integration. And in this section, we're going to be able to find volume using integration. So the shapes created by a lathe have these circular cross sections. So this one right here looks like a donut to me. So the center's cut out, but there is definitely a volume there. Each of these are 3D shapes, and they are circular. If I were to cut them, you can definitely see the circle there. Some of them have wider centers or larger centers cut out than maybe this one on the left. But overall, it's a circular shape that we're trying to find the volume of. So there is a theory to this, and the idea relates to slabs or slices. So if I were to have some solid and I cut that solid into slabs of equal width, think of slicing a loaf of bread. If I take each of those slabs and put them together, that would give me the volume of the entire solid. And so each of those slabs has a volume, and adding all of those little volumes up would give me the volume of the total solid. If we were to take wider width, look at this picture here on the right, we have wider slices or thicker slices. This approximation wouldn't be as accurate as if I were to take thinner slices like what's shown here on the left. So the thinner the slice, the more of the slices I would need to get the shape, and adding all of those up would give me a better approximation of the volume. What I've just described is the idea of a limit. And instead of taking limits all the time, we're going to do it faster by using the idea of integration. And that's where the definition of volume goes. The definition of volume states, let S be a solid that lies between x equals A and x equals B. If the cross-sectional area of S in the plane P through x and perpendicular to the x-axis is A of x, where A is a continuous function, then the volume of the solid S is the integral of A of x evaluated from A to B. So how does this relate to the lathe that we were talking before, or those circular 3D shapes? Well, we're going to be doing volumes of solids of revolution. And so we're actually going to be taking functions and revolving them around an axis. And by doing so, the cross-section area that each of these shapes has is going to be circular. So solids of revolution are obtained by revolving a region about a line. In general, we calculate the volume of a solid of revolution by using the basic defining formula, which is volume is equal to the integral of your function A of x evaluated from A to B, or if doing this in terms of y, the volume is equal to your function A of y evaluated from C to D. And we find the cross-sectional area, A of x or A of y, in one of the following ways. If our cross-section does not have a hole in the middle, we call that a disk. So let me highlight that. And this disk that you have can be, come on. If your cross-section does not have a hole in the middle, so here's a cross-section of this 3D shape here. Notice it does not have a hole in the middle. This is called a disk. It's solid all the way through. To find the volume, we would need to find the radius of the disk in terms of x or y and use this area function, a equals pi r squared, in our integral. The reason we're using a equals pi r squared is because the shape that we've created is a circle. Now your radius is going to be your function that you're rotating around the axis. And the reason is your axis is in the center, your axis of rotation, and so you're rotating this shape or this function around the axis. So the radius is technically going to be different lengths at different x values. And so your function is what's going to define that distance for you from the edge of the shape to the axis of revolution. If the solid of revolution has a hole in the middle, the cross section would be considered a washer. To find the volume of this solid of revolution, we will need to find the inner radius and the outer radius and compute the area of the washer by subtracting the area of the inner disk from the area of the outer disk. So here we have the area formula for this situation. And when this happens, you'll take the larger circle's area, which we'll call the outer circle, and subtract the smaller circle's area, which we'll call the inner circle. So let's get an idea of what's happening here with this example at the bottom. So here we have a function on top and then a function underneath. And we're trying to rotate this around the x-axis. When we do that, here's my axis in the center. We took the outer function and rotated it. And then we took the inner function and rotated it in this circular shape. And you can see that the edge looks like a donut or a washer. And if I were to take a cross section anywhere throughout this shape, for example, right here, you would still have that washer shape to it, where you have an outer circle and then also an inner circle. So if I were to take that washer and look at it from above, we would have this outer circle and then this inside circle, and we would be taking the big area all the way through. All of this gray would be the big circles area, and we would be subtracting out the center portion, and that would leave us with this washer shape for our area. And so that's where they kind of get this large area function, the outer circle minus the inner circle. So now let's put all of this together into a process. The process for actually finding this volume of revolution around whether it be the x-axis or the y-axis, and using this idea of circles, whether it be a disc with no hole in the middle or a washer when there's a hole in the middle. There is a general process to follow. And the process is defined for us here step by step. Step 1 is to graph curves as accurately as possible. It is really important to be able to see a picture of what's going on. Step 2, sketch the rotation with a slice, and that slice is perpendicular to your axis of rotation or revolution. If you're going around the x-axis, so if you're revolving around the x-axis, dx means that's your thickness of the slice. That's telling you that your function must be in terms of x. And if you're going around the y-axis, your thickness of your slice is dy, so that's telling you you must be in terms of y. When you're defining your radius, your disk is going to just have one radius, that's your function, If you're doing a washer, if there's a hole in the middle, you will have 2, the outer radius and the inner radius. Step 4 is to determine your boundaries. Sometimes they are given to you, and other times you'll need to find intersection points. Step 5 is to set up your integral, which is defined here for us using that idea of area of a circle, pi r squared, for your disk, and using that idea of a circle essentially twice, pi r squared for your outer radius, and then pi r squared for your inner radius. Now, when you're doing the washer method, your outer radius, if you're doing things in terms of dx, is going to be your top function or the function above, and your inner radius is going to be the bottom function. When you're doing things in terms of dy, your outer radius would be the function on the right, and the inner radius would be the function on the left. So let's get to the examples. Example 1. So example 1 states, consider the area bounded by the straight line y equals 3x, the x-axis, and x equals 1. When the shaded area is rotated 360 degrees about the x-axis, we observe that a volume is generated. The resulting solid is a cone. Find the volume using calculus. So the first step of our process is to graph the curves as accurately as possible. And luckily for us, this is actually done for us. So this picture we have here, or I should say this graph we have here, is of the straight line y equals 3x, the x-axis, which is our horizontal, and the line x equals 1. So it's creating this shaded region here. And this shaded region is rotated, and this is the rotation picture here, around the x-axis. And so it creates that cone. So what I'm going to do is label our lines as y equals 3x, the axis, which is the line y equals 0, and then of course our vertical line x equals 1. So our vertical line, I'm going to highlight that by drawing that, and then of course our axis. Okay, so there's our general picture or our general graph, and we rotated this graph around the x-axis, so it's kind of rotating around there, and it created this cone. This cone is a disk because there is no hole in the middle, so we are doing the disk method for sure. And if you look, the next step of our process is to sketch this rotation with a slice. The slice is actually here for us. This yellow slice is going to be our dx here. It's showing us it's perpendicular to the axis of rotation, and so there is our slice, and it is labeled dx. Okay, so all of this together is telling us that we need to have everything in terms of x. We have it going around the x-axis. We have our dx, which is perpendicular to the x-axis, our slice there, and we have this function in terms of x. So let's do our volume for this 3D solid in terms of x. And so here is the disk formula. The pi and the r squared, if you recall, is your area of your circle. So this disk shape that we have here. So that's where that's coming from. So just as a reminder, that's the area of a circle, pi r squared. And we typically put the pi in front of the integrand sign, or the integrand symbol, because it's a constant, and so it keeps the integral less cluttered if you put the pi in front. So just as a reminder, try and keep your pi in front of your integral, and also this is the area of a circle that we're working with here. So we do need to figure out our radius. Now, as described in step 3 in the process above, it says to define your radius, and since we're using the disk method, our radius should be our function itself. And the function that we're really rotating here is this lovely y equals 3x. Okay, so our function is y equals 3x. So our radius is going to be 3x because that is being rotated around the x-axis. And if we were to kind of draw it, so you can kind of see how it's being rotated. Okay. Just try not to laugh at my pictures because they can get a little comical. They're not exactly the most elegant, particularly when I'm doing them on the computer. So give me a little liberty here, and I'll try my best. But anyway, so we have defined our radius. It is 3x. We have our graph. We have our slice. So we now need to determine our boundaries. So our boundaries are sometimes given to us, and sometimes we need to find intersections. This graph is intersecting here. So the line y equals 3x is intersecting the x-axis at the x value 0. And it is intersecting at the vertical line x equals 1. So those are going to be our boundaries because those are the cutoffs of this green region when x is 0 and when x is 1. So those are actually going to be our boundaries. So we didn't really need to do too much calculation there. It was more of just seeing where the edges of our region are. So now let's set up our volume integral. So volume is equal to pi. Our lower bound is going to be 0. Our upper is 1. And then we have our radius. Our radius, as we have written here, is 3x. Many times people will forget to square it. Don't forget to square your radius because you are making a circle there. And then put your dx on the end. So that's your thickness there. Okay, so we need to actually calculate this. So the easiest way is to expand this, take this 3 to the second power and the x to the second power. So let's rewrite this simplified. So the integrand from 0 to 1 with the pi in front. And then it would become 9x squared dx. And then that is relatively simple to take the integral of. You're going to add to your exponent and divide by the new exponent. So as you can see, that's what I did. My new exponent became 3. I divided by that new exponent, so 9 divided by 3 simplifies to 3. Don't forget to bring your pi, that constant pi that was in front of the integrand. Don't forget to bring that along. And then we need to evaluate this from 1 to 0. So let's do pi in front, and then plug our 1 in. So 3 times 1 to the third minus 3 times 0 to the third. Now, obviously, when you plug a 0 in there, that will, of course, cancel out. And we have pi times 3. And so my solution here is 3 pi. Now, we are dealing with volumes, so we do need some units on that. No units were specified in the question, so we are just going to keep it general and just write units cubed. Okay, so that's the first question, the first type. This is an example of a disk question. Once again, it's a disk because there is no hole or gap in the center of your solid, your revolution, around the x-axis. This is being done in terms of x because we are revolving around the x-axis, and the slice of our solid is perpendicular to our x-axis there. So now that we've seen an example of a disk, let's see an example of a washer. Example 2. A cup is made by rotating the area between y equals 2x squared and y equals x plus 1, with x greater than or equal to 0 around the x-axis. Find the volume of the material needed to make the cup. Units are centimeters. So, before we get into solving this one, let's just go back up and refresh ourselves with the steps. So step 1 is we need to graph the curves as accurately as possible. So particular case, in example 2, they have graphed it for us and they've even labeled them for us. This blue line here is y equals x plus 1, so that's one of the functions we are rotating, and then the second one is the parabola y equals 2x squared, and that is the black curve here. Now, it does say in the information for this question that we are dealing with x greater than or equal to 0, and what that means is we are basically working right of the y-axis. So we are working only in quadrant, and I need to get my pen to work, my goodness. Only in quadrants 1 and 4, so right of the y-axis, which is why this graph is kind of cut off at this vertical axis here. Okay, so we are working here, so we know that we're dealing with basically 0 and to the right. So next, now that we have a sketch of the graphs, the next step is to sketch the rotation with a slice. And remember, your slice is perpendicular to your axis of rotation. Okay, so this is also drawn for us, but if it's ever not drawn for you, a suggestion is to kind of use the idea of symmetry to help you get the general look of it. And again, I am doing this on the computer, so give me a little bit of leeway. I'm trying my best. So there's my general look of symmetry, kind of. And you can see that I've done a quick sketch. This does help you when you're doing your slice. So here's my slice that I'm drawing. Okay, there's my slice. And this slice is perpendicular to the axis of rotation. So I'm revolving this around the x-axis, and notice it is perpendicular. Also, this distance here, this dx here, is showing us that it is definitely going to be a washer because this area would be included. This section in the middle is not, and then this portion down here would be included. So in that particular slice, you can definitely see that there is that hole in the middle. So this is reinforcing the fact that we are dealing with a washer in this particular problem. Now this dx here, this is the thickness of my slice. It is dx, so that's telling me we're doing things in terms of x. And because we're dealing with a washer, I'm going to have two different radius. One is the outer radius and the other is the inner radius. So let's talk about those two, the outer radius and the inner radius. So when dealing with these, remember that your radius must be measured from the axis of rotation to the original function. So remember, you're talking about the distance from the rotation axis, or excuse me, the axis of rotation to the function that you're spinning around that axis. So that is your distance, and that's going to be your radius. So for your outer radius, you want to have, since we're dealing in terms of x here, my outer radius is going to be my top function, and then my bottom function is going to be my inner radius. So let's look at let's look at this picture and see how that makes sense. So here is, of course, the better image of of the rotation. So here's our axis of rotation right down the center, okay? And here we have the axis, and the longer radius, the larger radius, so to speak, is going to be your outer radius. You can see that the distance there is much greater than the distance from the axis of rotation to my inner function, which would be the inner radius. This is going to be the smaller radius length. So we would label them as the large uppercase R for our outer radius and the lowercase r for the inner radius. Okay, so outer radius is upper and lowercase is the inner. Again, if you look at this diagram we have here, the linear function is on top and the quadratic function is underneath. And so that reinforces the idea of your outer radius, in this case being on top, and your inner radius being on the bottom. And again, that's when you're doing things in terms of x. So what we need to do now is we need to say, okay, well, what is the function for this uppercase? What is this outer radius function? And that outer radius function is y equals x plus 1. And so that's what we're going to have, x plus 1, for the outer radius. The inner radius was the function y equals 2x squared. So that will be the second radius that we need to use for our washer method. The next step for us in this question is going to be step 4, which is determining your boundaries. So that is an important piece. Now in this one, we will need to find the intersection because in this graph here, you can see that our two curves do meet. Okay, so they are going to intersect. So that is going to be one of our boundaries. The other boundary was given to us when it said that we're working right of the y-axis. So we're cut off when x is equal to 0, but we need to figure out what this upper bound is going to be. So we do need to do a little bit of work for boundaries. So for our boundaries, we said that we are going to have to find the intersection of the two curves. Now again, I just said that one of our boundaries is going to be x equals 0 because that was our first edge of the cutoff here when x is greater than or equal to 0. So working to the right of the y-axis. So our one cutoff is when x is equal to 0, but we need to find that second one. So we are going to find the intersection, and that is going to basically be this point right here where these two curves intersect. So we're going to do that by setting our two functions equal to each other. So 2x squared is equal to x plus 1. And what you would want to do is bring everything to one side. So 2x squared minus x minus 1. And then this one you would want to factor. This one is factorable. So you would get 2x plus 1, I believe, and x minus 1. And when you set both of those equal to 0, one of them would equal 1 and the other would equal negative 1/2. Now, when x is equal to negative 1/2, that would not apply to this situation due to this restriction in our beginning information. X had to be greater than or equal to 0. So we know not to use that particular option because it doesn't adhere to this statement. So our upper bound is going to be this x equals 1. So our two bounds are going to be 0 and 1. Now, we have found the boundaries, so let's figure out what the next step is. So we are now on step 5, which is to set up the integral. When you're setting up the integral, something I want to point out, notice that the pi in your integrals is out front. I had mentioned that before, but you can certainly take that out in front because it is a constant. So remember the rule, you can take your constants in front of your integral. So it does help simplify your calculations when you do that, because then you're just not constantly writing pi all the time. So pi can be in front because it's a constant. So that is just something to note so that you don't get confused as to why pi is not with the r squared or your radius squared. Okay, so let's go back down to our question. We need to set up our integral. So we have volume is equal to pi, and then our integrands bounds are going to be from 0 to 1. Those are what we found before as our boundaries. And then we need to set up our two radius. So our outer radius is x plus 1. So that should go in parentheses because you're squaring this radius separately from the inner radius. Now my inner radius is 2x squared, so 2x squared, and that's being raised to its own power of 2. So each of them is the power of 2 separately. Do not put them together. Now let's simplify the inside of this integral so that it's easier to actually calculate with. So now we have the volume equal to pi of the integral, or times the integral of x squared plus 2x plus 1 minus 4x to the fourth. So we need to take the antiderivative of that, which would be pi times 1/3 x cubed plus x squared plus x minus 4/5 times x to the fifth. And what you did to get this again is you add 1 to your exponent and then divide by that new exponent. So that's what we did. And at this point, we need to take this and evaluate it at 1 and then subtract the evaluation. So we need to plug a 1 in for all of those x values and then do the same for 0. So the first part is the evaluation at 1, and then we're subtracting the evaluation at 0. This is really just going to be subtracting 0 because everywhere there is a place to plug in 0, it would cancel to 0. So the first term would go to 0, the second, the third, and the fourth. So each of the terms would go to 0, so that entire evaluation would be 0. So then we would just need to simplify and get our final answer. So our solution is 23/15 times pi. And you might just automatically try to start writing units cubed, but they did tell us that we are dealing with centimeters for our units. So we need to remember to write centimeters cubed on this one. So cm cubed instead of just our plain old units cubed. So that is an example of a question where you're doing a washer. You've had to find the two different types of radius, the first being the outer radius and the second being the inner radius. And this also showed you the idea of finding boundaries. When rotating something around the x-axis, I visually see something that looks tipped over on its side. So in this example, too, to me it looks like the cup is turned over on its side. And if it were to be filled with water, the water would be coming out. When rotating something around the y-axis, however, so going to the next page in your notes where it says theory, now we're talking about rotating things around the y-axis. And to me, when this happens, it looks like the image is standing upright. So in this disk example here, to me it looks almost like a thimble is placed on a table and it's standing upright. And in this washer example, to me it looks like a vase is standing upright, maybe on a table. So that's how I sometimes visually organize things in my mind to help me better understand what the end result of this volume shape is going to look like. Now, when revolving things around the y-axis, the slices that we take are going to be perpendicular to the y-axis. So the slices are no longer going to be up and down, but rather right and left. So the slices in both of these images are perpendicular to the y-axis. And so these slices are going to represent your dy, or your thickness. So in both of these methods, again, disc and washer, you'll be following the same process that you did before, graphing the functions that are given, expressing or drawing the rotation on the graph to help you better visualize what's happening, drawing the slices through the 3D rotation so that you can really see where, in terms of what variable we're working with. Again, when you're doing rotations around the x-axis, you're in terms of x, and now we're doing rotations around the y-axis, so we'll be dealing with terms of y. And when you're dealing with a disk, there is no hole, so there's one singular radius. When dealing with a washer, there should be two, the outer radius and the inner radius. That outer radius is often your rightmost function or curve, and then the inner radius would be the left function or curve. Then determining your boundaries. When dealing with x, we did boundaries basically from left to right. Now we're doing boundaries from low on the bottom to high on the top. When we're dealing with terms of y, once you find the boundaries, you can set up your integral and then start plugging away and calculating to get the volume of this 3D object. Or in other words, our solid of revolution. So once we've done all that, you will have calculated your answer, revolving something around the y-axis. So the process is, again, very similar, just now we're doing things in terms of y instead of in terms of x like we did in our prior two examples. So let's get started. Example 4 says, find the volume of the solid of revolution generated by rotating the curve y equals x cubed between y equals 0 and y equals 4 around the, and please change this to y axis. I should have changed that in the notes prior, and I failed to do so. So let's just change that to the y-axis, because that was the intention for this question. Okay. So again, we're following that process. Our first process here is to graph, which is actually done for us. We see this lovely cubic function of x cubed, and it's going from the function y equals 0 to the line y equals 4. So I'm just going to label y equals 4 and y equals 0 because I have a feeling I'm going to need that information. Okay, so we are rotating this around the y-axis, so our axis of revolution is definitely this vertical axis. So let's try to draw what this would look like when we actually revolve it. And over here on the right is where we see this done for us. So lucky for you, you don't have to try and draw. It's always a bit of a challenge to try and do that, I know, so we will spare ourselves in this particular example. So using that idea of symmetry, it's the same on both sides. It would have that circular shape to it. So we're definitely seeing this. And when you draw your rotation, we have to try to remember to draw a disc or our slice or our slab. So here is our slab here, our slice through. And this is showing us, because it is perpendicular to the y-axis, that this is our dy. So we will be doing everything in terms of y for this example. Now, the next step is going to be finding the radius. So we need to look at this function here that we drew are cubic. And because we're dealing with a disk, there is no hole or gap that's happening here. We are only going to have one radius. And you know what? I was remiss to mention before that we should really have another restriction on our graph here. We should really have the vertical x equals 0, so this vertical line here, because you really do want to restrict this region from all sides. So I'm just going to write that in there now, x equals 0. I should have had that written before, and I didn't. So anyway, let's talk about the radius. So the radius is going to only be 1 since we're not dealing with a hole. It's a nice solid disk. So the radius again in this case is your function. So my radius is going to be represented by the function, and again that's the distance from the axis of revolution to your curve. So my radius is my function, and my function is currently y equals x cubed. But this is not okay written like this because we are supposed to be doing things in terms of y. And this function is written in terms of x. So we need to rewrite this so that it is solved for x. And to do so, we are going to take the cubed root of both sides. So we would get the cubed root of y, which in my opinion is easier to write as y to the 1/3. Okay, now we have our radius in terms of the proper variable. The next step is to find our boundaries. And they are actually given to us in this case. When doing things in terms of y, you're going from low to high. And our low boundary was given as y equals 0, and our high boundary is given as y equals 4. So I'm going to go ahead and make a note that we have found the boundaries, which wasn't too hard to find them since they were given to us. Again, sometimes you might need to find the intersection, but luckily for us, we didn't have to work too hard this time. And so there they are. So we are pretty much ready to set up that integral and start some calculations. So the general setup of our integral hasn't changed in the sense that our revolution is still that circular shape. So we're still doing the pi r squared idea, the area of a circle. This would need to change to dy, so let's change that now. Since we are doing this around the y-axis, all of our functions need to be in terms of y, and our integral needs to be in terms of y. So we are ready to set it up. So we're going to use that radius, that area of a circle idea, putting the pi out in front because it's a constant, using the radius that we found written in terms of y for our r squared here, and then our a and b values are going to be the boundaries. So let's set that up. So here we have it. Volume is equal to our constant pi times the integral from 0 to 4, which were our boundaries, of our radius, which was expressed in terms of y to the 1/3, squared, so our radius is being raised to the second power, dy. Now, I would suggest simplifying this. We do have a power to a power here, so you can certainly simplify that to make your calculations easier. So that's going to become y to the 2/3 dy. And now you can take the integral of this. So add 1 to your exponent, divide by that new exponent, and then evaluate your expression with the boundaries of 0 and 4. So here is the next step. We've taken the antiderivative. So we added 1 to our exponent, divided by that exponent 5/3, which gives you the coefficient 3/5, and now we're going to evaluate it. Again, when you evaluate it from top to bottom. So you do the 4, 0, and subtract. The evaluation at 0, of course, would equal 0. So this is essentially a 0 there. And we just need to find our final answer. Now this answer would obviously not come out as a nice simple fraction. because of that 5/3. When I plugged into my calculator just to triple check myself to make sure that it didn't come out to a nice simple fraction, it definitely came out to an irrational number. So there has to be another way to simplify this. And if you notice, our exponent here is a top-heavy fraction, 5/3, so it's an improper fraction. That can actually be expressed, and you can write that as 4 times 4 to the 2/3, because really this 4 is to the 3/3 power, right? Because to the 3/3, that's the equivalent of 4 to the first, or just 4. So we can actually pull a 4 out of there to help us simplify this a bit. And when we do, the expression can be rewritten as, I'm going to kind of write it out to make it really clear, pi times 3/5, which was our coefficient, times 4 times 4 to the 2/3. All right, so we can definitely combine these two to get us a nice simple fraction of 12/5. And then I'll put the pi after that, and then I'll just write 4 to the 2/3 after. And I do not believe, I better double check, but I do not believe units were specified in this question, and they were not. So we're going to keep it general by writing units cubed. So you can either write units cubed or u to the 3rd power, that's fine. So that is how you would revolve something around the y-axis when dealing with a disk, which means you do not have a hole or gap in the middle of your solid revolution. So once again, now that you've seen rotations around both the x-axis and the y-axis, you can tell that the process is generally the same for both. The only difference is what you're doing your function and integral in terms of, whether it's in terms of x or in terms of y. So steps 1 through 6 should follow pretty much the same process every time. When you give your final answer, again, you want to give an exact answer. Do not do decimal. So even in the last example we just did, when we were talking about it being an irrational decimal, the proper way to do that was to give it as an exact answer through fractions. So once you have this process down, you should be good, and hopefully you'll be able to get through the first parts of the homework for this section. Good luck!